is you. And you jumped in on very short notice because one of our speakers did not make it. So please give him an extra round of applause for being our last speaker today.
Thank you, guys.
And he will be talking about a topic that we didn't cover in depth at this conference, evaluation. So stage is yours.
All right. So I start with this. This is me. I'm currently an applied researcher at the Content Understanding of Search Science of eBay. I joined eBay around towards the end of 2021. Before that, I was a PhD in linguistics. I did both formal and computational steps. And if you recognize some of these icons, you know the sort of things I've been dealing with on a daily basis. And this little nice graph down here, this is taken from a dissertation. Forget about that. We're not going to talk about this today. All right. So I'm going to talk about evaluation here today. So suppose you have done all your hard work. You now have 2 or more, even 3, I don't know, however many models, embedding models that you have that you want to take into the A/B test. But obviously you don't want to do a ABCDEFG test. That's just gonna be too expensive, right? So before you make a decision that you will regret later, probably it's a good idea to do some offline evaluation first and to choose just maybe 1 or 2 to go with the A/B tests. And for the standard evaluation, we usually assume these are the ingredients that we have. So you have a set of documents, you have a set of queries, and for each query document pair, you have a relevance judgment of some sort. And we're talking about ranked retrieval here, right? And now you have your ingredients and you have all of these standard recipes, such as precision and K at K or recall at K. And so these things are focusing on the relevant items at a certain window from top to the kth results. And if you want to monitor the situation at a bigger scale, or you want to see a bigger picture, you can even plot your precision recall curve like this. And on the left-hand side, you have your standard interpolated curve, and on the right-hand side, you have your average curves across several queries, so it looks smoother. And if you don't want to look at a graph like this, probably you want something that is more condensed. You just want a single number. So you can go with a mean average precision, or you can go with your NDCG. So probably something you have already noticed here is that all of these things rely on your judgments about the true positive and true negatives, right? So I want to know which of these items are actually relevant and which of them are not. Same thing goes here. You need a precision, right? And also this particular factor, this particular factor here, this is the case when you're dealing with a case, it is non-binary judgment. You have a score, you have maybe a high relevance score, and you might encounter a low relevance score. But anyway, you're dealing with a true positive and true negatives. At least we're assuming that is the case from your judgment. All right, so the question is, where the hell did I get all these ingredients from? I have all of these nice recipes. Where the hell do I get them from? And first of all, you can go with human annotated data sets. And if your org can afford to hire an army of annotators to do some annotation for you, that's pretty nice. But if you want to maybe for some reason to update your data set on a routine basis, and maybe that is not a very good idea. It's going to be very costly and very time consuming. And the second option, of course, is you can go with some generic benchmarks, such as MTEB here. But this is just a benchmark for evaluating the quality of text embeddings in general, not just for retrieval, right? So retrieval is just a tiny section of this benchmark. And many of the data sets used here are also showing up here in this Spire here, or beer, I have no idea. And many of these data sets, if you take a closer look, they are for general question answering, such as Quora, And some of those, just the last time I was checking, are even from the medical domain. So good news for the pharmacy people, but maybe not for e-commerce people. And so that's the situation. So eventually, you probably want to resort to something that is more specific to your own organization, to your own use cases, right? So maybe it's a good idea to look at your historical user engagement to get the sort of relevance data. So this is what you would typically do, I suppose. With when I'm talking about historical user engagement, basically what you're doing is you're looking at across several search sessions, right? From maybe, I don't know, some certain time window, across the duration maybe of a month or several months, right? So, and you're looking at all of these queries, and you see whether or not for a certain query, the user has engaged with certain items or not, right? So for example, and by engagement, I mean things like conversion or clicking. Maybe clicks is not a very good idea if you want to avoid clickbaits. And by conversion in the context of e-commerce, you might have things like putting into the cart or actually checked out, or for eBay specifically, we have things even like bidding, offering, and something else. And so, all right, you might have some engagement data that allows me, I like this item, I have purchased this item, or I didn't even bother with this item. You might have some signals like this, and you might use this kind of data to create a data set. I will say, oh, so this query and this item, they are relevant, or this query and that item, they are not relevant, they are irrelevant. This is how you might want to go. But the thing is that probably you want to be very careful about how you compose such a data set, right? So while when you see engagement, that might entail relevance. In most of the cases, you can confidently believe so. But when I don't really see engagement, or when I see low engagement, does that necessarily imply it's no or low relevance? That's the questions, right? So think about two scenarios here. For example, in the first scenario, what if your user never reached page 2? They just drop out after viewing something on page 1. Actually, there is something. What if something actually that is relevant that occurs on page 2, right? So there is no user engagement between their query and that particular item on page 2. But that doesn't necessarily mean that this query and that item they are irrelevant. So probably you want to do is that you want to take impression into consideration when you are creating your data set. That's one way to combat it. But what if your user just maybe just jump to page 3, or they're skipping page 2 very quickly? You might even get some impression in signals in your data set, but they actually didn't really pay any attention to page 2. So things could happen. You can come up with a lot of scenarios. So this is where you want to be really careful. And what's even more important is the scenario 2, like null and low queries. When you are searching for something, so for this particular example, I just did it a few days ago. I used the name of my manager, and there were no exact matches found on eBay. Good news for him. And instead, I got 2 books, not even authored by him. And in this particular case, well, this might not be a very realistic query, but in real life, especially for a platform like eBay, where a lot of users are searching for some very niche items with the hope that they might be able to find them there. And if they're not able to get anything, that's going to be very frustrating. But in most of the cases, when they're not able to find anything, we actually have those things listed on the eBay somewhere. They are just not able to find the magic words to summon the demon or whatever. And so in this case, if you're evaluating your models, you don't really have any positive or negative signals associated with this kind of queries. And I would not even know. I don't have much insights about what's really going on with my model, right? So, okay. So to summarize, with all of these scenarios, probably you can even come up with more scenarios. And these are the risks. So I might end up, if I just rely on my historical user engagement data blindly, I might end up reinforcing current bias or failures in another way to put it. And I don't have much insights about models' performance on non-low queries. So what we can do instead is to think about what I really want to get out of a embedding-based retrieval model. So what I really want is well-behaving of query embedding and well-behaving of item embedding. And these two embeddings, query and item embeddings, they really cooperate. That's what I really want. So I'm assuming this particular brand of embedding-based retrieval where you have this two-tower architecture or biencoder architecture, however you call it. And your query your query encoder and your item encoder might have some overlap in terms of their computation units. It really depends on what goes into these encoders. I don't want to get into the details about that. How you want to train them is not included in this talk. But as soon as you have these models, you should be able to get query embedding out of your query input and item embedding out of your item input. Right? So that's what I'm talking about. The well-behaving of each of these and their cooperation. So these are the things we really want to evaluate. Now, before we proceed, probably you want to ask, and you should ask the question, does it really make sense to talk about the similarity of one tower when you have a two-tower structure like this? That's a legitimate question. So conceptually speaking, you might reason like this. You think about if two queries, they both kind of recall the same set of items, they should somehow be relatively similar to each other. And on the other hand, if the same query is getting you this a set of items, they should also be relatively similar to each other, right? If everything is well behaving. And in reality, we do have some empirical evidence to show that this is from an entirely different domain of application. But if you're familiar with CLIP, that's also a two-tower encoding architecture. And it's even a two encoder architecture with two different modalities. So one is from the image and the other one comes from the text. And actually, if you only use the visual similarity part of this encoder, it actually does a pretty decent job for our visual similarity search functionality of eBay. This has been productionized, I believe, at around May of 2022, but this blog post come up really late, a year later, on March this year. And here is a different project. Also, we're using only visual similarity from this part of the story, and we use this to augment, to do label augmentation for visual classification, and we got some very decent results. And this is the tiny paper for this year's ICLR. And so let's get back to the main story. We start with the query embeddings. So the well-behaving of query embedding, by that I mean similar queries should have similar embeddings. That's a safe assumption to make, I hope. And for this particular task, we are very lucky to have this data set of a list of similar queries. These are annotated by human, and also a list of dissimilar queries. And if our model is doing a decent job of embedding queries, then I would suppose that the distance I computed using my query embeddings, I computed for the similar queries should be distinguishable from the distances I computed for dissimilar queries, right? So if you plot, to visualize this, if you plot the distances of similar queries and the distances for dissimilar queries on an axis, you should somehow to be able to separate them. In an ideal world, if your model is really doing a great job, they should be completely separable, right? And so what you can do here is that you can use the distances that derive from your model, from your query embedding, as the input for something like an SVM. You can train a linear classifier or something, trying to draw a separation boundary, a classification boundary to maximize the classification accuracy. And the maximal accuracy that you can get is a pretty good measure of how separable these points are, right? So these are two real models that we're evaluating. Model A, in this case, has got an accuracy, a classification accuracy of 80%. And on the other hand, the other model, Model B, has only an accuracy of 68%. And if you fit those points into a Gaussian distribution, you can actually visualize this, right? So on the left-hand side, the model for Model A, the distances we computed for negative items and the positive items, the overlap is smaller. And on the other hand, the overlap is much bigger, right? So much about query embeddings. And for item embeddings, probably I want to do something similar. Similar embeddings should imply similar items, right? So that is, what do I mean by item similarity? That is relatively something not so easy to find. So we can proceed with some approximation. So you can choose a very, very low standard. If two items are similar, they should at least belong to the same category, right? If your organization has a category hierarchy, a taxonomy or some sort, or knowledge graph or some sort, to classify all of your items. If they are neighbors, if they are very close embeddings, then they should at least belong to the same category. While this is a very low standard, but actually we found it's quite useful when we are evaluating these two, the Model A and Model B from the previous page. And as you can see here, as we are doing our k-neighbor search for Model A, this is the k equals 10, the 10 first nearest neighbors for each item in the data set. The k equals 15 and k equals 20. The same setup here on this is the right-hand side. So on the left-hand side, you see that for Model A, the median of the agreement read is around 0.7. And as the number of neighbors increase, it drops a little bit, 0.67 and 0.6. Whereas for Model B, the number starts with 0.5 and it drops to 0.47 and 0.45. So again, in this case, it seems that, again, the Model B is probably not as robust as Model A in terms of item embeddings. And now the last part, and probably also the most important part, is that the item embeddings and the query embeddings, they should really cooperate with each other to give you good search results, right? This is the thing that you actually care about. So in this case, again, you need a set of items, however you want to sample them, and you need a set of queries. And for our particular experiments, this is a set of around 50K null and low queries. And our items set size is about around 50 million. And you want to utilize some of your organization knowledge about your queries and items instead of relying on historical user engagement data to say whether or not two things they match or not. And again, we're talking about ranked retrieval. So in this case, we're just retrieving the k nearest items for each query. The k is much less than the total the cardinality of the item set. Obviously, I cannot get all the 50 million nearest neighbors. I don't want to sort everything. What we're doing is around the k is around 80. What kind of knowledge I can use? The kind of knowledge, again, the simple knowledge that I can use is that for every listing on eBay, I know as a ground truth the categories of the items, right? So if you're open any item page, you will see this the category tree here. It's just the path in the tree, and you will be able to see the leaf categories of the item. And also, we have this prediction of the dominant category of your queries. When you're searching for something, we will try to predict the category of the things that you're searching for. So you have your predicted query category, and you have your ground truth item category. So, right. So in this case, I can talk about the agreement between the query category and the item category, right? So if I'm searching for, I don't know, maybe iPhone, but if you're returning me some results like t-shirts, or I don't know, some home and garden, maybe furniture, then something must be going wrong. And another kind of knowledge, it really depends on what your organization has. So in this particular case, from some other team within the search science, they have trained some query item relevance model to predict the relevance of query in the item. I don't know exactly what goes into their training data, but we're including this just for comparison purpose. So with this kind of thing, then you can talk about the category agreement rate at K. Right, so you're just looking at for the first K results, and this is just a binary function, whether they agree or not. By agree, I mean the category of the query is a ancestor of the category of the document or item. And more generally, this is a generalization of this one. You have a function, it could be a model, it could be something, could be handcrafted heuristics, that is going to give you a relevance score between a query and a document. And here you want to be very careful because you don't want to rely again on your historical data. Otherwise, we're just returning back to the starting point. And to give you some concrete example for this particular query here, I don't know exactly what this is. And this is what I found on Google. It seems to be kind of blades. I have no idea what this is. And this is the recall from the Model A. In terms of category agreement, you can see that, well, for the predicted category of this query, we predict this as, eBay predicted this to be factory manufactured. And if you look at all the first 20 results retrieved by Model A, only the first 3 items are of this category. Everything else, it's crazy. So you have books, you have jackets, you even have rings. So I don't know what the hell is going on here. And this is the result of Model B for the same query. A lot better. You see a lot of these things showing up, a factory manufactured. And this one is actually nice also. It's blades. It is actually blades. This is just one query, and you want to do this over our 50K queries. And so you can get an idea about as the recall size increases, how fast the relevance or the quality of your recall drops. That's what you really care about. In this particular case, the Model A is not doing as well as Model B. Oops. Right, so especially for this category agreement, for the Model A is dropping very fast compared to Model B. And for this case, for the predicted relevance, the difference is probably only minor, but how you interpret this minor difference, that's a different story. They are kind of giving you the same conclusion as this one though, right? You see the Model B is doing better than Model A, even though it's slightly better, but I don't really know what slightly means, right? I don't really know what slightly means. So to summarize this part, what you want to do is that beyond history, you might want to think about the well-behaving of your query embedding, which means the query similarity and embedding similarity, they should translate to each other. And the same thing goes for item embedding. And you want to see that your query and item embedding, they really cooperate. And for this particular example, we illustrated the case of category agreement and predicted relevance. And you might come up with something that is more specific for your organization, depending on what sort of resources, organization knowledge you have in your case. And for this particular case, for example of Model A and Model B, what we can learn from here is that, well, Model A might seem to be more robust in these two metrics, but not so well here. So that's why you're seeing, well, now we're having Model B also in A/B testing. And but if in some cases where you see two models, they behave similarly in terms of the query and item embedding cooperation, these two guys can actually break the tie, right? If everything else is equal, then I can use these two things to make a wiser decision about which model I want to proceed with. And also with these more specific metrics, you can kind of get some insights about what your model is doing and how you want to improve your model's performance. Like for this case, for example, in this case, what the Model A is doing is that when I'm searching for something, it is getting me all kinds of results, right? So you know where you want to invest your efforts to improve at least the category precision of your item embedding. So that's all I have to talk about. Thank you.
Thank you. Do we have questions? Yes, we have.
Hello, thank you for the talk. It was really insightful. My question is, when you are comparing the similarity of the categories and you're checking, how much of a diversity of categories are there, have you thought about taking into consideration whether the diversity of categories that are there are very similar to each other? Like if the list of categories that you see are all very different in terms of, name, but they're kind of from the same general area, as opposed to a list of categories that, here's automobile parts and here's clothes.
That's a very good question. So you actually, this is a very rough version. This is some work of a part of evaluation framework we're still developing at a still very early stage. You probably want to look at your category tree and to do some more smarter calculation of distances by looking at maybe the distances within the tree or whatever metrics that you have. Yes, that's a very good idea.
Thank you.
Yes, please.
My question is, how do you predict the relevance between the item and the query?
Oh, that's a very good goddamn question. They didn't tell us. We've been asking them several times. From what I know, the rumors is that they are still using some user engagement data, but I don't know exactly how they are evaluating their model. That's the problem, right? So I don't really care how you train your model. If your model can be evaluated to do reasonably well on human judged data sets to give me a reasonable answer about whether or not certain query and items are relevant, then I can use your model without asking too much questions. But that question is something I also want to know about. Yes.
We have one online question. Are there A/B test results for model A and B? And what was the ending of that story?
Model B is still going on. I don't really know about know about the progress. And even if I know about it, I probably am not allowed to talk about it. Yes.
You mentioned that you were given a data set of similar queries.
Yes.
Do you have any ideas in how this could be created or anything, how this was created?
The rough ideas is they somehow sampled some queries and they asked human annotators to go through them, whether or not this is similar queries or whether or not they are different. Yeah.
More questions? I guess we can then let you off stage with a last great round of applause.
Thank you.